Thanks a lot for having me, for this invitation. Yeah, I'll tell you about some work that I did with some fantastic collaborators. Peter Kraftschuk and Sridhar Pal, who might be on Zoom at some point, but I don't see him yet. And there was also a simultaneous paper by James Bonifacio that has some non-trivial overlap with our results. And so as you probably understand, I'm not a mathematician, rather I'm a physicist, and I am mostly interested in quantum field theory, specifically conformal field theory. And if you don't know conformal field theories, there are some very nice rich class of quantum field theories in general dimension, which can be studied fairly rigorously, starting from some basic set of elementary axioms. This is an approach known as the conformal bootstrap. It's an approach deeper rooted in the representation theory of the conformal group, and that's what I've been mostly working on so far. And this work that I want to tell you about today, it kind of started when my collaborators realized that there's some very close analogy between those methods in the conformal bootstrap that we use to constrain conformal field theories and what you guys have been doing, or some number theories have been doing related to the spectral theory of hyperbolic manifolds, automorphic forms, and things like that. So what I want to tell you about today is how we used some of these conformal bootstrap methods to prove new constraints on the spectra of hyperbolic surfaces. And well, when we were writing this paper, we sort of thought that all this is completely new and that mathematicians don't know these methods, but we have come to realize that that's far from the truth. Actually, various incarnations of this idea have appeared in the math literature, for example, by Bernstein and Reznikov, and also Akshay and other people have proved bounds on L functions, which use this moment method. I think that's what it's called, which is very closely related to what I'll tell you about today. But nevertheless, I hope that there'll be some non-trivial new things, and I hope that we can sort of start some discussion between the conformal field theory people and number theorists or whoever else is interested. And I certainly think I have a lot to learn from you guys. So we'll see if the converse is true as well.
Certainly will.
All right. So let me just start with the basic setup and the basic statement of the results. So yeah, I'll mostly talk about hyperbolic surfaces or hyperbolic orbifolds. So the setup is we start with the upper half plane, which of course has this canonical metric dx squared plus dy squared over y squared that is being acted upon by Maass transformations. So the group of Maass transformations is PSL2R, which will play a central role today. And you can think of the upper half plane as the quotient of PSL2R by the maximal compact subgroup, which is just the rotations. Okay. Okay. So that's of course very well known. And to specify a hyperbolic orbifold means to specify a discrete subgroup of PSL2R. So gamma is going to be a discrete subgroup of finite covolume. And in most of the applications, I also take gamma to be cocompact, so that the orbifold is a compact orbifold. But also many of the things that I'll say apply in a non-compact finite volume setting. So the discrete cocompact subgroup. Okay, and then you can take the quotient of the upper half plane by gamma, and you get the hyperbolic orbifold. So if gamma has no elliptic elements, this is actually a manifold. But if there are some elliptic elements, it's an orbifold. Also, some of the things I'll say apply in higher D, but let's just, for concreteness, let me stick to. Okay. And then you can formulate the Laplace equation on this orbifold. So the Laplace operator in the upper half plane is y squared dx squared plus dy squared. And Laplace equation takes the following form. So what we want to understand is the spectrum of eigenfunctions and eigenvalues of the Laplace operator on the surface. Of course, a problem that many people have thought about, including some in the audience. So HI are the so-called Maass forms. So there are some functions in the upper half plane which are invariant under gamma. And lambdas are the eigenvalues. So starting from 0, which corresponds to the constant.
This is kind of like a boundary condition.
Yeah. Well, it's you don't need to specify boundary condition because this thing is sort of compact. It has no boundary. So HR some smooth functions in the upper half plane.
You're saying
it's periodic boundary conditions. That's right. So 0 is the first angle, and there is some non-zero gap to the first non-trivial eigenvalue, and then infinitely many eigenvalues going up to infinity. And well, of course, lambda 1 is of special interest, for example, because of the Zellberg conjecture and so on. And today I'll mostly focus on this lambda 1. So what's the main result?
The fact that you don't have a continuous spectrum.
Oh, it's because I'm assuming it's compact. Yeah.
Okay.
I mean. Should I write? Okay, let me over here. Not everybody is going to see, right? So let's go. Okay, so the basic practical outcome of what we did is some universal upper bounds on lambda 1. Here's direct some upper bounds on lambda 1.
Looking for the lights here.
Yeah, they seem to be out. Maybe.
The reason they're out is.
Oh,
I mean, it can be turned on.
No.
It can be turned on if people need it.
No, I just pretend to see these days.
No, I think you can use the left-hand border.
Oh, okay.
So we can get the right side. Yeah, yes, you can use it if you want.
Yeah, I wasn't sure if people who are sitting over here would.
They'll shut.
They can move.
Okay. All right. Well, I'll leave it there. So first, one thing that comes out of this analysis is a universal upper bound on lambda 1 among all hyperbolic 2 orbifolds, which are compact. So yeah, just to not stop repeating the phrase compact hyperbolic 2 orbifold, I'll just say orbifold. That's what it will mean.
What is an orbifold?
Or orbifold, it's a manifold which can have some orbifold singularity. So that happens when gamma has some elements of finite order, and the manifold will have, for example, for SL2Z, there are these 2 orbifold points of order 2 and 3.
But sorry, you said genus 2?
No.
Genus 2 will appear soon, but this is universal. So
This is 44.88. I don't.
888 goes on. So this is true for all compact hyperbolic.
He wants to see that as if he's seen that number before.
That number is, it's not 44 points, 40, I don't know what it is.
It's 44.888.
That's what I was looking for.
It's bigger than a quarter, if you will.
Yeah.
It's bigger. That's right. All of these things are bigger than a quarter. So these particular results don't say anything about the non-compact cases, but yeah, the spectral identities will derive also apply to non-compact situations. So then when genus is 2, I think that maybe what Akshay was asking, then we have a bound which is 3.8. I guess I don't have to. I should say we derived all these bounds using linear programming on a computer using some numerics, but then you can actually check them rigorously using rational arithmetic. So what I'm writing, the digits should be rigorous. For genus 3, there's an upper bound which is 2.67848. Yeah, and okay, these look like some random numbers, but maybe the reason why they're interesting is that they're actually these bounds are nearly saturated by some known examples. So this bound is nearly saturated by the smallest orbifold, which is the 237 triangle. So derived by Zigo, that hyperbolic orbifold, the smallest volume is the 237 triangle surface. So you get it by gluing together two triangles with angles pi over 2, pi over 3, and pi over 7 together to get something which is smooth away from the orbifold points. And this one has an eigenvalue about 404.8.
Have you included two triangles?
Just
one above another?
You take one. So you take two triangles like that. This side is identified, and I identify this with this, and this with that.
You take the reflections in the half the triangle and you double it up to make it orientation preserved.
Yeah. Yeah. So it's a.
So you could say it's a Neumann eigenvalue for the triangle.
Oh, it's just a Neumann eigenvalue.
Yeah, that's not having
Just do it with that.
This, yeah, I think that's right.
Neumann boundary condition.
I see. I'm sorry, I never thought of it that way.
You get reflection, so I guess.
Yeah. I don't know. I think
Yeah, so everything is orientation preserving. PSL2 is orientation preserving, and gamma is an orientation preserving group. So all the surfaces are orientable. For genus 2, this seems to be nearly saturated by the Bolza surface, which is the most symmetric point in the genus 2 moduli space. So the Bolza surface has eigenvalue lambda 1 about 3.83889. And in genus 3, there is the Klein quartic, which is this is an example of the orbit surface, which are surfaces that does maximize the automorphism group. And so the Klein quartic that has lambda 1 about 2.6779, I think. Yeah, so in all of these cases, the bounce is not quite saturated, but saturated to a fairly high number of decimal places.
There's a numerical component to this. I mean,
Yeah,
I know that in the bootstrap, people use computers to linear programming kind of things.
Yeah, that's exactly what we did. And but then once you use the computer to do linear program, you can rationalize everything. You can rigorously check that these are correct bounds.
Now, is this the way mathematicians do it too when they get bounds?
no. He's got a new method. No, he's got a completely new method. But
Okay.
You write lambda 1, which for the first one, which agrees to as many decimal places, it seems, as you've written there. But you're not claiming that your linear program actually gives that number like it did for E8, right? You're not claiming that.
Yeah, we are not. Yeah, we are not claiming that. It's we haven't decided whether if we extrapolate to so a priori these are some infinite dimensional linear programs, and you need to truncate, and you need to extrapolate to infinity to see what the bound in principle converges to, and we are not sure whether in this limit of infinite truncation it converges to the actual eigenvalue.
So you're not in the position as you were, or as it turned out you were at Biasovska, where the linear program is known to have a solution which saturates.
That's right. Yeah. I mean, in this case, the spectra are something more complicated. For the sphere packing, the spectrum was very simple, so you could hope to have an analytic proof. Here, I mean, maybe there's an analytic proof, but okay.
These are asymptotic, which means they're accurate.
No, that's
very high
right.
precision, right?
These bounds are obtained for some finite truncation of the linear program.
Yeah. So, but you can get lower bounds like that here for these particular surfaces, like Bolza surface.
Lower bounds?
Yeah, lower bounds. In other words,
I don't know.
You're saying other people computed the Bolza surface to that accuracy.
Yeah, other people computed this. Eigenvalues using
your bounds are all
finite element method.
upper bounds, right?
Upper bounds.
So,
Okay, let me just give you a sketch of the method. So so deeper rooted in representation theory of PSL2R. So the first thing is to look at this space that sure number theory is not.
Okay, before you get into that, just because I've read your paper, I think the theorem that I find very attractive, which you haven't stated, is he actually describes exactly what the image of lambda 1 is under all orbifolds, which is a struct. It's like a Markov spectrum or something like that. Maybe you should state it. I think.
Okay, I was going to state it at the end, but I can state it. I can state it now.
I find it very interesting.
Yeah, the theorem that well, I don't think we quite proved it, but there are some.
We'll discuss it afterwards.
Okay.
You
Well,
prove more than you think.
okay, yeah, you can ask. You can ask what is the image of lambda one?
That's
As you scan over all the orbitals.
The spectrum of the spectrum.
The spectrum of lambda one, and what we have essentially proved or conjectured is that this is the answer.
So you're varying over genus 2 or general genus?
General. So there's a 4 to 4. That's the bound over there. This is the maximal, and there's the 2, 3, 7 triangle. And there are several more isolated points. Should I forgot? Let me just make sure that I don't screw this up. Okay, then there is a point where so the isolated points must be 3 punctured spheres because everything else is moduli. So the 3 punctured spheres have orbifold orders 3, 3, 4, which is actually the same as the 2, 3, 8. Sorry, 2, 3, 8. This one is a double cover of this one. And there's another one which is 2, 4, 5. Okay. Well, and here's a continuum that starts at about 15.8, which corresponds to a 4 punctured sphere, the smallest 4 punctured sphere, which is 2, 2, 2, 3. These are the orders of orbifold points of the. So that we essentially proved that this must be the image. There's a couple of isolated points, 23.1 and 28.1. And the reason you have a continuum here is that there are 4 punctured sphere you can deform and then generate.
Just conferences. Yeah, that is something that I never guessed, and it's an amazing statement, and you've essentially proved it. That's the image of lambda one under all.
That's
You don't want the line.
It also
I understand. Yeah. So you get continuous stuff and then.
Yeah, he's got an interval, and then he's got 3 points, and he knows which guys hit those.
But don't you need some kind of magic function to prove that, to get the 15.8?
Yeah.
Or you don't get like a 15.8001 or something?
Well, we have a numerical approximation of this magic function, but it's an open problem to construct the exact analytic magic function. I mean, for any of them, it's not special.
What is magic? Is that the where Sofska? Is that what you mean by magic?
Yeah, the extreme null function.
Okay. In the infinite dimensional.
Yeah, but maybe this statements don't make sense to everybody in the audience. So let me.
Okay, sorry, I just to me that's quite. Since you're talking to people who've thought about this for a long time, I've never seen that formulated for.
So you can actually prove that I mean, by deformations that there's an interval there where sort of
Right.
there are no gaps, right?
Right. It's like a band in.
Yeah.
But it's not block wave theory at all.
No, of course.
Okay, so here's a sketch of the method. First, you look at this space. It's a nice automorphic space that has a G action by right multiplication, and the spectral problem on the orbifold just corresponds to decomposing this into unitary irreducible representations. So that's how you translate everything into representation theory. And then we look at these quadruple product overlaps where you integrate over G mod gamma. And what you integrate are 4 functions, or product of 4 functions in discrete series representations. So these are in holomorphic discrete. These are anti-holomorphic discrete representations.
What is the?
Oh, yeah, this is maybe just a sketch. I'll explain everything in detail. And
This is the analogs of correlation function.
yeah, these are like correlation functions of a conformal field theory. And then you can expand these products using completeness in the Hilbert space. And you can expand it in 2 different ways. Either you expand it like that, or you expand it like that. In this channel, you get holomorphic stuff. In the other channel, you get the Maass forms. So you get spectral identities that are of the form sum over holomorphic forms equals sum over Maass forms. And then you apply linear programming to it's infinite for each holomorphic form. There are infinitely many such identities because you can vary this function within the irreducible component corresponding to that holomorphic form. And
that's an identity. You're going to explain inequality.
yeah, I'll explain
inequality.
It's
a linear program.
Yeah. Okay, and that's basically the main idea. That they use linear programming to prove these bounds, starting from these spectral identities.
Sorry, I have a naive question. We could try to analyze this by setting up some kind of linear programming thing starting from the trace formula, right?
Mm-hmm.
Would that be related to this? Like that would be a naive way to try to bound latitude.
I don't really know that much about a trace formula, but I think it would be an independent constraint. I think it's a kind of interesting question to what extent these constraints are independent, whether these imply the trace formula. In conformal field theory, there is an analog of the trace formula, which is modular invariance of the partition function, and that is an independent constraint.
No, I think, okay, we can discuss it afterward.
So do you have a notion of primary fields here, that kind of thing?
Yeah. It's the group is PSL2R, so there are some lowest weight representation. So okay, so that was maybe a bit high level, and let me now revert back to sort of explain things in more detail at more elementary level. So yeah, some representation here. Before saying things about representation theory, I'll just make some remarks. Okay, so we have this orbit field specified by gamma, and up to isomorphism. This gamma is specified by something called a signature. I was already using this notation extensively before, but just for those who didn't follow, signature is just a collection of the data, which is the genus of the surface and the orders of the orbifold points. So there are p orbifold points, these are n1 up to np are the orders, and this is the genus. But to specify the surface, you need to give more than just the isomorphism class. You need to give it the embedding of gamma into G, and then there can be some continuous moduli in 2 dimensions. So in more than 2D, most of rigidity tells you that there are no such moduli, that specifying isomorphism class is the same as specifying the embedding up to conjugation. But in 2D, there are these moduli. Okay. But there are things which are robust under moduli, and that's the holomorphic modular forms. Holomorphic forms they're just holomorphic functions in the upper half plane, which transform covariantly in the usual way. So f of z is cz plus d of r. So this is a weight 2k modular form, and I'll use the notation k to mean this. Okay. The weight is 2k, but maybe sometimes I'm going to say weight is k. So, okay. And one nice thing about these forms is that you can count how many there are of each weight just from topology. That's what the Riemann-Roch theorem buys you. The Riemann-Roch theorem says that, well, it's a consequence of it, that if mk is the number of linearly independent weight 2k forms, then number is 2k minus 1 times g minus 1. So it's just the function of the signature. There's some formula like that, which depends on the verse. And so, for example, n1, the number of holomorphic differentials is just the genus, and 2 is the number of quadratic differentials, and that's equal to the dimension of the moduli space. That is 3G plus P minus 3, and this formula generalizes to arbitrary K. Okay, very good.
By the way, I wanted to ask you, when you go to higher genus, what happens to the eigenvalues? Is there a pattern? Do they come down or what?
They come down, and we didn't find any other higher genus example that would be nearly saturated, but maybe that's just because we don't really know we don't really know what point in the moduli space should maximize the eigenvalue.
They have to come down to a quarter when he gets to it.
So our bound actually
And they're monotone? Or?
our bound doesn't seem to go to a quarter at large genus, but we are not really using all the constraints. This is just some subset of constraints, and probably if you use all of them, you would come down to a quarter. Okay, so now finally the representation theory.
It may not be monotone because there may be, like in some genus, some extra symmetric surface that there isn't in a genus plus 1. I wouldn't be surprised if it was.
Okay, so the basic idea is to work with this space, G mod gamma, and you have a Hilbert space, which is the space of L2 functions, and this G mod gamma. Now the G acts by right multiplications, and this is a unitary representation of G of PSL2R. Some function inside V, so I know it's so the sum range is left invariant, and the norm is just the R integral. And well, the reason why it's a unitary representation is that you can now act by right multiplication of these things, and the hard measure is pretty here. I can take some G inside the group and send f of G to G killer. Okay, of course, what we want to do now is to decompose this into irreducibles. So L2 gamma, when this is compact, when gamma is cocompact, this thing is also compact, and there's a discrete decomposition. There's no Eisenstein series. It's just and here is the decomposition. There's a trivial representation which appears once. Then there is a sum over the Maass forms of the principal or complementary series. I'm going to denote both of them by P, even though they can be complementary in principle. The lambda is less than 1/4. And then there is a sum over the discrete series, which corresponds to the modular forms. And the discrete series comes with its conjugate. These are self-dual and these are not self-dual, but they appear in dual pairs. But the nice thing is that the spectral problem is now stated as a representation theory of statements.
What is dual here?
Is the dual representation?
What's the duality?
Well, it's the space of linear functionals on this. They're also unitary. So the duality is, I guess, just the inner product gives you the dual. Okay, I don't want to embarrass myself with some but yeah, this is just a space of linear functions on that, and they are not equivalent for the discrete series. This is a lowest rate representation, and this is a highest rate representation. So as I already said, the identity is just constant functions. Then these principal series, they are one-to-one correspondent with the Maass forms. And the discrete series, they correspond to the modular forms, where I should say that the lambda for the principal series is just the Casimir eigenvalue. So it's a way to label these representations, and the discrete series are labeled by K, which is the weight of the modular form. Forms. And the D bar, they correspond to the complex conjugates of modular forms. That's why they come in pairs. Now the question is, if I just give you some random collection of these representations, can you tell whether they can come from some L2 G mod gap? And the point is that in most cases they cannot, and that's why we can prove these bounds. And the reasons why usually they cannot is that, well, from our point of view, it comes from the existence of the fact that you can multiply these functions. So each of the elements of this thing is a function, and you can multiply the functions pointwise. This product structure respects the G action. So it's an additional constraint on this spectral data, as well as on the triple overlaps of functions.
Here you only use 4 functions.
Yeah, the two.
And you never do more.
The constraint comes from associativity of the product. So to implement it, you need 4 functions. So you have product. All the things which you can multiply are, for example, smooth functions. The general elements of the L2 space, if you multiply them, don't really stay in the L2 space, but if the function is smooth, you can do it. So you have a map like that, which just takes 2 functions, sends it to the pointwise product, which is the same. And well, this obviously commutes with the action of G. And well, as was formulated very crisply by Bernstein and Reznikov, this leads to some nice simplifications. Let me give you a sketch of this. Yeah. So let me denote Ri is going to be some abstract model for an irreducible representation that appears in L2 in this L2 space. Okay, so it's some variable G, thought of as abstractly, not necessarily embedded in that space, and Ri is just the embedding of this irrep into our space. And also, let me denote like Pi, the projection in the space onto the factor corresponding to Ri, the summand, direct summand. So this is just the orthogonal projection to the image of Ri. And so the point that I want to get across is that the G invariance means that this product structure can be captured by some discrete set of data. And the discrete set of data are the triple product integrals of elements of these arrays. And that comes from uniqueness of trilinear functions on irreducible representations of G. So let's see how that goes. Well, what does it mean that we have a product? Well, the product is on the space of smooth vectors in a pair of these representations that you're mapping to gamma. So you can take some vectors V1 and V2 in Ri and Rj, and well, then we map our V1 to gamma and Same thing for 2. So now this is some function on G mod gamma. That just this means. And next we can just insert the identity of completeness. We have this statement of completeness that the sum of the projectors is 1. So we now insert this. And the whole point of this this gymnastics is that this object is extremely tightly constrained by representation theory. It's a G invariant map from Ri cross Rj to Rm, and the space of such maps is finite dimensional for the conformal groups, and for PSL2R it's at most 1 dimensional.
So what is PM again? Is it?
PM is the projection.
Oh, it's projection.
On the irreducible component. So this thing is fixed.
So that's your trilinear thing.
Yeah, this thing is fixed up to a single multiplicative number, and that number is the triple product overlap.
What if we have multiplicity of Laplacian eigenvalues?
Well, for each of them, there's going to be one number, but that's not a statement about representation. So if there's multiplicity, that just correspond to multiplicity of multiple values of this m. M ranges over all the irreducible factors inside L to G mod gamma, so it's still true.
Okay, I see.
Is it okay?
Yeah, I guess.
Okay, so the point is that if we ask about these invariant maps from Rj to Rk or Rm maybe, then we can fix some. If there exists such a map, it's unique up to rescaling. So let's just fix one such map, theta Ijm. There's maybe some canonical choice, but let's not worry about that. Then this vector is just a constant multiple of that map. So it's some constant Cij. I'm going to denote it Ijm bar.
What special structure are you saying about the RI? Are these like the primary fields or not?
Sorry, what's
the RIs that you're using? Are they the analogs of primary fields?
The RIs are the irreducible representation. So that the primary field is like one element of the representation, and then you can translate the primary fields to some other points. And
just the irreducible,
just
irreducible representations. And you're basically multiplying them or transferring them up. Is that the same?
It's not as, I don't think this tensor product. I'm just saying that
it's a multiplication.
It's just not. I mean, probably you can extend this map to the full tensor product, but I don't really need it.
Yeah.
Okay, so the whole point of this discussion is that this product is now captured by these numbers Cij and bar, and this is something that doesn't depend on the surface. It's purely a representation theoretic object. Okay, so that's how you capture the product structure in terms of some discrete set of data, which are I already said it, but let me write it. These are this is the triple overlap integral, between three holomorphic functions. And the constraints that we use come from imposing associativity of the product, which will give you some bilinear constraints on these C's that also depend on the spectrum. So to implement associativity, you take 4 of these representations, so I, J, K, and L. And you construct this chain-invariant map, which is just the integral of the product of these things. One, 3, 4. So this is G invariant, and now you can expand it using the product in several different ways. So for example, you can expand the product of V1, V2, V3, V4, or V1, V3, V2, V4, or there are three such choices how to pair these up. So let's make it. Let's choose this pairing. You get a double sum over these irreps because each of these products gives you a sum. I'm just using this replacement. So you got C, I, J, and bar, C, K, L, and bar. And then you have this integral. And then we use this uniqueness of the invariant map. IJM, V1, V2, Rn, KLN, V3, V4. Yeah, but of course this is simple to evaluate because it's only non-vanishing when M and N are dual to each other. So it's just the pairing on the representation. So you can only the diagonal terms survive. This is just the canonical pairing between the representation and its dual. So all these things are defined purely abstractly without referring to the surface. So this object doesn't depend on the surface, and it's analogous to the conformal block. It's like I mean, it literally is the conformal block in some cases. So it's the conformal block for PSL2R. Okay, and now you can do this gymnastics in several different ways to get some non-trivial constraint on the C's. So, for example, what we did was to expand it like that, sum over M. But you can also do with that.
Let's just tell you how you're pairing them up, right?
Yeah, that's right. And this is well, this is what in the CFC literature we call the conformal bootstrap equations. It's an infinite set of coupled equations which constrain the Cij case and the spectrum of irreps in this Hilbert space. And well, if I was to write this. Let me just.
You're just getting a family of identities by doing this, or what?
Yeah, you got a huge family of identities which are labeled by. Well, they're labeled by choice of 4 irreps I, J, K, and L,
Yeah.
and a choice of 4 vectors V1, V2, V3, V4 inside of these irreps. So let me call this the conformal block V1, V2, V3, V4. So the editor that we will get from here is okay, you can imagine. I was just going to write the identity that this object equals to the same object by some permutation of the labels.
So just basically using some kind of associativity, right?
Yeah.
You just group them stuff together in different ways and doing different expansions.
I mean, yeah. So the thing is that. Recently, there's been resurgence of interest in these equations in the CFT literature and in higher dimensions because people realize that, contrary to appearances, these equations are really powerful. And in fact, they often lead to some sharp bounds on conformal field theories, or at least nearly sharp bounds. And there's like a general belief that any true fact, any true fact about the spectrum in the Cij case is a consequence of these equations.
So when I look at those coefficients, do they, you know that they get small as you go higher up?
Yeah, I mean, there are some, for example, there's a bound by Pierre Sarnak, exponential bound on, well, that's I guess in the case of three Maass forms, but there are some known bounds on the case.
Anyways, making an L2 expansion.
Sorry, so you're saying that the reason that you don't consider, for example, 6-point correlations or higher is because intuition, just that it's expected that these 4-point correlations should kind of give you everything. Is that correct?
Well, associativity of the product is equivalent to this identity for all quadruplets of representations. And whether that's the most efficient way to actually implement it is a question. I mean, there could be something that you can more easily get by looking at 6 points, even though in principle everything is a consequence of 4 points.
Yeah, I guess I was just asking why should associativity only give you sharp bounds? But maybe this is just a stupid question. I'll think about it. Thank you.
Well, I think what the answer to your first question is that the consistency of 6 points is a consequence of consistency of 4 points. If you implement consistency of 4 points for all quadruplets of representations. I think I'm a bit.
Yeah, that's okay. Yeah, you go ahead.
Yeah, so as I said, people in the conformal bootstrap think that these equations are really powerful, and I just wonder how what number theorists think of it. Like, are they the ultimate answer to everything, or are they just one small fragment in the whole possible set of constraints?
They don't imply Lindelof as far as we know.
They don't imply?
They don't imply the best possible bounds for the Cij case.
But if people, of course, for example, try to, the point is that there are really many coupled equations that you can scan over all the various choices of I, J, K, and L. That's actually something that has only been done in the CFT literature to some small extent. Like some people have only looked at a finite set of these IJKLs, and one thing that should be done, I think, is to sort of look at infinite sets of IJKLs at the same time. All right, well, I'm gonna have to.
So you're saying actually this is not enough then, or not?
Well, this will be enough to get the bounds that we proved on the paper,
but let's see. You haven't explained the linear program.
Yeah, I haven't explained the linear program. So yeah, I guess I'm gonna have to skip some steps, but let's just apply this in the very simple case when Ri, Rj are some discrete series representation of weight k, and Rl are its dual. So we are fixing a fixed modular form on the surface of weight k, and we are writing this equation. Then, well, if you work with the unit disk model for the discrete series representation, you arrive at an identity. So now I'm skipping some steps that I want to explain, but I think I was too ambitious. The identity that you get looks as follows. So there is a function of a single complex variable, g of w, and this function admits two different expansions. One is a sum over non-negative integers of some positive number times some known function okay, so this is a sum over modular forms. Yeah, let me first write it and all right, so the left-hand side, the function of a complex variable, which is holomorphic away from the cut from 1 to infinity. Holomorphic, and on one hand, it has an expansion in terms of modular form. So here, dn is the norm, the Peterson norm of the nth ranking Cohen bracket of the modular form. So we remember we fix some modular form f with weight k. And this is the norm of the nth ranking Cohen bracket. G is some hypergeometric function. W. Okay, so this is just a sum over these holomorphic objects. And here on the right, okay, it's just this weight. And here's a sum over the Maass spectrum. CAI is this overlap integral. Between the modular form, its conjugate, and the ith Maass eigenvalue. H is another hypergeometric. It's 1/2 plus IT minus IT 1. Okay, where lambda is 1/4 plus the squared. That's the spectral identity that I was talking about at the beginning. It's
So these infinite sums are convergent in.
Yeah, they converge. They certainly converge pointwise in this region of holomorphic. We didn't prove it, but they probably converge uniformly in every compact subset of this. So basically, the type of convergence you need. I mean, each of these functions is holomorphic in that cut plane, and you want the sum of the holomorphic functions to converge to something holomorphic.
I'm guessing the formula you wrote for CAII is actually for it and not its square.
Oh,
Inside.
thanks, yes. All right. Now, how do we use this to prove bounds on lambda?
Sorry, let me ask one question. So you got this from using some vectors in this DK, which depend on W.
Yeah.
Which vector did you pick, or how did you know which family of vectors to pick?
Well, we picked the family that we normally pick in the CFT context. So in the unit disk model, the vectors would be when you represent discrete series in terms of holomorphic functions, if you're holomorphic outside of the unit disk, then the vector is this one. So it's a function of W tilde with a pole as W of order 2k. So the primary.
That's the primary.
The primary would be.
Oh, I see it.
Would be W equals 0, and I translate it to some other point.
Okay.
But now we have 4 of them. And W is the cross ratio of these.
Kind of maximally localized in some sense, these vectors.
Yeah. But ultimately, we are just expanding to set up a linear program. We are just expanding this identity around W equals 0, which is the same thing as inserting k-finite vectors. So we're not really doing anything fancy. We are just really using k-finite vectors to prove these bounds on lambda 1. So just to set up the linear program, well, you can sort of invert this equation. And write, you can invert the left-hand side and write this norm of the n20 coin bracket as a sum over the Maass eigenvalues. Now, let me include the identity as the 0th term in the sum. And there's some polynomial of order n, which is computable from these functions. And also another important thing is that dn vanishes for n odd. N odd because f is the same as f, so and this thing is for n equal odd, it just vanishes, which reflects the symmetry of our original choice, that the Ri, Rj are the same thing. So we have these. So now so we can consider some linear combination of these polynomials, Pn. So Q is a polynomial in lambda, and well, if we sum the polynomial with these weights over the eigenvalues, using these identities, you get is just a sum from 0 to capital N over n even, because the odd terms drop out, of alpha n dn squared. Okay. So if you can choose your polynomial in such a way that it's positive, non-negative from some point on, such that these alphas, even alphas are negative, you get an upper bound on lambda 1. Let's just imagine we can choose these alphas such that the following conditions are satisfied. First, Q at 0, which is the identity, is 1. Second, that Q is non-negative for all lambdas above a certain gap. And finally, that all the even alphas are non-positive. Then, if you can choose alphas, so these ones are satisfied, there has to be, everything here is non-positive. There has to be at least one negative term on the left-hand side. So there has to be a lambda which is smaller than lambda star. So this gives you there's an upper bound on lambda 1, which is lambda star. Okay.
I know I'm a little faster, so this seems like the key point here.
Well, we are using these identities.
Yes.
They come from the.
Yeah, I understand.
From inverting this equation, and now I'm using them to put an upper bound on lambda star, and here are the steps. Let's just. The goal is to take some linear combination of these identities.
Okay.
Okay. And here is linear combination specified by these alpha n's, and you need to choose them such that we get a contradiction unless there is a lambda below a certain.
Okay.
Yeah, I mean, I've prepared much more stuff. Yeah, maybe let me just conclude by so this is like a very simple linear program, and let me just tell you what are the consequences various values of k. Because there are some further consequences beyond what I said. So well,
So you're really only using so far a very small fraction of all of the.
yeah, right? Exactly. It's very small fractions. So in this way, you get a lambda star as a function of the weight of the modular form that you're using, and this bound is increasing with k. To get the best possible bound, you should use the minimal k that a given surface has. Well, so let me k1. Let's call k1 the minimum value of k that a surface has. Now, k1 is bounded by 6. It's 6 precisely for the 2, 3 p triangles. Well, in that case, so when we set k equal to 6, we get the bound that I advertised at the beginning, the 44 point.
So to be clear, another way, you run the linear program, you get your bound, and the only input you had about gamma was that it's got a 6 dimension that you can make the holomorphic forms of weight k to k. Anyway, the first time it's not 0, and that's so the bounds are independent of gamma. And that's why you get a universal bound.
Yep.
In this first case, right?
Yeah, that's right.
And the linear program, it's like Elke's cone, where of course it's saturated in E8. You put the test function to be positive up until the value at which you're trying to find the shortest eigenvalue.
You
don't put any other condition beyond. Yeah.
You put it. So you said it. You normalize it at the identity, and then you say it's positive above certain.
And below you say nothing.
Below you say nothing.
Yeah, because that's what they did different to people before computers. Before, Levenstein, and these guys put in a specific test function, but they didn't run a linear program. It was incredible that it's saturated, as you are finding. Yeah, it's kind of remarkable.
So let me just conclude by saying what these values are for various values of k, because it's really simple setup. For k equal to 6, it's nearly saturated by the 237 triangle. This is 44.9 or so. Then the bound, when you use the k equal to 3 modular form, is about 23.07, and that is saturated nearly by this 334 triangle, which happens to be the smallest triangle whose k1 is equal to 3. Okay. For k equal to 2, we get this 4-punctured sphere, the 2, 2, 2, 3, that appeared on the plot on the left, where it's about 15.79. But this one has a modulus, and the bound seems to be saturated at the most symmetric point in the moduli space of this 4-punctured sphere. And finally, for k equals 1, does anybody want to take a guess? What is the saturating surface? It's something whose smallest weight modular form is k equals 1. And it's actually the smallest such orbifold. It's a torus. But the torus needs to have 1 puncture for it to be hyperbolic. It's the puncture of order 2 at the most symmetric point again, and it's about 8.46. Then to do higher genus, you need to sort of make this into a matrix problem where you use multiple different Ri's, Rj's. But I don't really.
So you get all these relations from what you were just putting on.
Yeah, it's just this linear program gives you all of these numbers, and they agree to a pretty good precision with the lambda 1 for these cases.
So if the genus is 2 or higher, the fourth one there, the genus is
the fourth.
They're all genus 0 except the last one. Right?
Yeah, this one has genus 1. That's the smallest.
And so it's already dropped below 15, so it's only genus 0 that can potentially upset you at 15.8, right?
That's a good question.
I mean, that's the only place that you're having trouble because you don't need saturation to prove that picture at the top because you know your candidate and you know your bounds to some accuracy. So you know you have to drop under, so it's all rigorous. But at 15.8, your best bound with one, sorry, what's your best bound with genus 2? Sorry, genus 2 we don't have to worry about. 1 or higher we don't have to worry about.
Yeah.
Genus 0.
Genus 0, we've only done this bound with a single modular form of weight 2, but you could imagine inputting the other modular forms, which maybe have a
You should bootstrap further.
Yeah. No, there are many simple things many simple ways in which you can extend this. I think it's kind of striking that the bounds are nearly.
Sure.
Okay, we are currently thinking about higher D hyperbolic manifolds, and also I'm trying to understand the non-compact case, like where there's an Eisenstein series and so on, and maybe the role of Hecke operators and all of this setup. I'm sure you guys probably understand it much better than me. Okay, let me stop here. Thank you.
So this linear programming idea was used for by Elkes and also in
Right. Yeah, there this the start. So here the starting point was this associativity, and for them the starting point is the Poisson summation formula.
Oh, okay.
Well, in fact, going back to my earlier question, so the trace form, Hilbert trace formula is very formally analogous here to the Poisson summation with the lambdas dual to the lengths of the geodesics. And actually, maybe the Bolza or Klein things are extremal for the length of shortest geodesic or something.
Yep.
So sort of suggests trying to do linear programming with the function in the Hilbert trace form.
Yeah.
Does that at least seem like something one could try, or is there
definitely. It's
there you have fewer free variables, so to speak. You just have this one function.
Yeah, it's something we've discussed with my collaborators, but we haven't gotten around to actually doing it.
But what's really interesting here is if you write the trace formula, you would probably write it without the weight K forms because you can separate it out. You would think that's the one to use. But what's really remarkable is his use of holomorphic forms.
Well, that's true, but perhaps just the weight zero trace formula will.
That's if you ask me to compute it for any one of these, but so if you're giving bounds which are independent of gamma, that is very similar to Elke's cone, who take this Poisson summation, as you say, and then they drop the fact that there's a lattice, it's gone, and then it's just a radial extremal linear infinite dimensional linear program for spherical functions. And then the incredible thing is it's sharp there, as they found by saturating, and then this magic function, as somebody called it. So there's a sacrifice, and the amazing thing is you throw away the lattice, and then you recover the sharp bound from the linear program. It seems you're doing something similar here, incredibly, throwing away gamma, just keeping the holomorphic forms and the 4-point structure. So I'm really interested to know if you think this saturates here.
Yeah, it's something we should really understand better to run it even to higher.
I mean, when you run it further and further, does it get closer and closer? Well, I guess nobody's computed the number for you sufficiently accurately.
The thing is that at first it converges exponentially fast with this capital N, and then it slows down, and I don't know whether it stops or whether it just becomes a power law. Yeah, we need to explore that.
But your goal here is to toy model of the bootstrap, right?
Yes.
And so what might you like to understand mathematically in this toy model from that point of view?
Well, I think that the interesting thing here is that we have an exploit realization of solutions of the conformal bootstrap equations, and that's something we don't have in a conformal bootstrap. There we just have the equations, and except for some trivial cases like the free theory, there is no exploit realization. So the great fantastic thing would be to learn like what is the analog of solving the Laplace equation, But for CFT, like here, you can either solve the Laplace equation or you can run this bootstrap. But for CFTs, we don't know what the analog of solving the Laplace equation is. We just have these equations. So that's kind of like a long-term goal to see if there's some exploit realization. But yeah, it's.
Let me turn that question around a little. I mean, as you know, in the Euclidean case, where there's a lattice and higher dimension, only in 24(8), and I guess what, 2? And 2, nobody's ever managed to make this work, but somehow it's a miracle that in those dimensions it works. And here, so do you have some intuition as to when you're going to saturate from your physics point of view? Like you started this, I would have thought you would never saturate, but you have. So, and in the conformal bootstrap, where I think you only supposed to get estimates, is there any situation where that conformal bootstrap is supposed to nail the answer completely?
Yeah, there are some situations, but they that's so far only happen for these sort of trivial theories. Like we call, for us they would be trivial, but that would be actually the case that maps to the Azov-Skas magic function, where the spectrum is very regular, equidistant set of norm square. And well, there are examples like the 3D Ising model, which people have bootstrapped to a very high precision, and I'd be very surprised if you could get, if the exact saturation is true, if you use just a small set of these equations. Like people have used.
If you keep on increasing the size of the
Yeah,
equation, then you should.
yeah.
You know, it would be surprising if you didn't. Right?
As I said, people sort of believe that if you were infinitely powerful and could put all of these equations on a computer, then you would get the
But is it the best way to do it? That's another question, right?
No.
There's a choice of which equations you decided to use, right? Which actually was mentioning how you choose these particular ones.
Mm-hmm.
So there's you have some insight or some intuition about what you might be able to handle, because in general this is a huge, confusing.
Yeah. Well, yeah, people have usually used the representations which have the smallest sort of energy, the low-lying ones, the low-lying spectrum. That seems to work pretty well.
I still want to push you on this magic function, because I think it was a shock to Elkis and Cohn, me, and people who that Vysotsky could write down the extremal function in an infinite dimensional linear program, and you separately have done that. So when should we expect that to happen? I just repeat the question. Here you're not convinced, but why did it work there? Is there a physical reason to work there? Was it just an obvious function to write down?
No, it wasn't obvious, and I think it's still not obvious, even in retrospect. It's why it worked there.
But your presentation is I think easier than Vysotsky's. It's a rational function, right?
Yeah.
That's very.
Okay. Yeah, but that's just a change of variables. Okay,
is there a slew of infinite dimensional linear programs that come from a natural class of problems for which it's very rare to write down explicitly an extremal for the infinite dimensional linear program? I mean, it was done. There's one that was done here at the Institute by Berling and Selberg. It's a one-dimensional problem about L1 function and a characteristic function and an extremal function bounding it above and below, band limited on the other side. And they wrote down the explicit linear solution. It's called the Berling system. And it's Berling. Selberg, I think, rediscovered. But that's one dimension. It's kind of, and in a way, that's what I think Elkis and Cohn were always looking for, is they wanted to find the analog, and that's what she found, and that's what you found. So the question is, what's going on here? Okay, so
I don't have much to say, but I think this is a candidate where it could be true, and we should push it to see if it's actually nearly saturated, and then maybe look for the magic function. But maybe the next obvious candidate is the two-dimensional sphere packing, where it has, as you said, it hasn't been done.
You've looked at that.
What's the wait a minute.
Sorry,
you've looked at that from your point of view. Two dimension.
Not very seriously.
What's the 2 dimensionals here? I mean,
Two.
Huh?
Two is, it's well known that two approved the best.
that's
Yeah,
right.
but to prove it using this linear program.
To prove it using the linear program, it's the, yeah, okay,
So far, that's sort of just out of range. Things don't converge.
I see.
The other interesting thing there is the largely asymptotics of the Kononokis bound.
Okay, but that's
That's
actually, I think Nina there is an expert. But I don't, as far as I know, nobody has improved in a serious way. Levenstein and Boltansky, although so Dari might have, he's written a paper on that.
Yeah.
I mean, I guess you were talking about high dimensional packings, right?
Yeah, right.
All kinds of questions we don't have.
So the question is just to improve that.
Well, yeah, so the conformal field theory should be like a big source of such linear programs, which may be saturated if you use enough of these equations.
I have a question about the test function Q. So it's a polynomial of degree n, right? Capital N. Is that true? Like your test functions are.
That's exactly right. Yeah, Q.
Yeah. So if you let capital N to grow these alpha i's, are they gonna converge to numerically? Do you observe any convergence of alpha i's? Because in the case of Noam Elkis, in the case of Elkis and Kohn, so they do get convergence numerically for.
Yeah, I'm not sure. I mean, the where alphas converge is sort of like a basis dependent statement almost, but the Q converges.
Q converges in your.
Converges to a smooth function, which is double zeros at the. That's actually something
exactly like the other one.
Yeah. Q has a simple zero at lambda1, and then it double zeros at the higher lambda. So you can actually
just like it does in other.
you can actually use this linear program to read off the higher eigenvalues of the 237 or 237 surface.
Oh, I see.
Yeah, fantastic.
Thank you.
I guess it has to vanish if you're going to get it that accurate.
It has to vanish. It has to be positive. So it has to be some zero of even order. We have a picture of that at the end of our paper if you want to take a look.
Okay, thank you.
Okay, are there any other questions or comments?
So for the 2,3p case, do you just know exactly what lambda 1 is for p more than 7? Like, how do you know that falls in the interval?
That falls on that it's over here, or
yeah.
Sorry. Well, yeah, that's a great question. Well, you could I guess run the numerics, and then you would find that all of the higher p's are somewhere in here. So actually, 238 is over here, and 239 sits exactly at the start of this continuum. But you could also try to do it using the bootstrap. So for example, in our paper, I think we use the fact that when you have 23p for p greater than 7, then the next modular form is weight 8. So there's always, the first one is weight 6, and the next one is either weight 8 or weight 12, and it's 12 only for this one, for 237. And then we use this to put an upper bound on everything which is not 237, which is 23p for higher p. And well, but that one, the upper bound is somewhere here, right? Because 238 needs to satisfy. But you could play these more complicated games and maybe eventually push all of the 2,3p's into the continuum.
So you mentioned that somehow these sphere packing, I'm sorry, these optimization and these linear programming problems simplify in some extent, in the sense that you observe that you can solve them exactly in the case when the dimension is regular. I mean the spectra of these problems are regular. Can you elaborate on that a little more? Like,
well, you know, there's essentially just there's like one continuous family of examples of the exact solution of this linear program, which is the one that I guess in our paper with Miguel Paulos, and the two special points of that correspond to the Vyazovska's extremal functions in 8 and 24 dimensions. And well, in this only example that's available, the spectrum is regular.
If you're interested in an arithmetic sequence.
Yeah, it's just an arithmetic sequence. So, you know, if the spectrum is not regular, so something like this, something chaotic or arithmetically chaotic, then
it's interesting that these are all arithmetic, and so the spectral are probably Poisson, just for your information, high up in the spectrum. So not GOE.
So wait a minute, so you're talking about the high spectrum of all these?
Yeah, right. Because that's what we talk about. He's saying that the magic function in the other case, the spectrum was very regular. Yeah, of course, the spectrum ain't regular, but it is not GOE because he's for 237 at least. That's an arithmetic congruence group. And
general ones would not.
Schmidt, people have computed, Schmidt and Book only computed high eigenvalues of that. And they follow Poisson.
That's for the 237, you said, right?
yeah, the simplest,
All of those are.
yeah, the simplest one that's not arithmetic is 345, I think.
I can't remember.
Yeah. And well, it doesn't show up here, but probably you could nail it using some more complicated.
Yeah, but probably maybe the sharpness is connected with the arithmetic.
I mean, I was wondering if there was an explicit or conjecturally an explicit connection. I mean, if you somehow managed to, maybe this is a harder problem, if you somehow managed to know what the high-lying spectrum looked like, would that help in any way with searching for these optimizers, or would it suggest anything about these optimizers?
Well, I think to find an optimizer is at least as hard as having an analytic formula for the spectrum. The optimizer will know about it because it will have double zeros on the spectrum. Oh, I don't know. Maybe there could be something more implicit. You know, the spectrum is principally determined by gamma. So you could determine the optimizer just by gamma. Yeah, I don't have much intelligence about this.
Okay, thank you very much.
Thanks.